Okay, so this video is section 8.7 calculus. This is the first section in unit 4, indeterminate forms and L'Hopital's rule. Okay, so an indeterminate form, what an indeterminate form is a form from which we can determine nothing. So for example, in the past, if you recall, if we were doing a limit and we got 0 over 0 or infinity over infinity, we said that those were indeterminate because you could not determine anything from 0 over 0. Okay, so for example, in number 1, okay, where it says find the following limits, if I go to find the limit as x approaches 2, we put 2 in for the x. Okay, and we're going to get 4 plus, whoops, that's an 8. 4 plus 4 minus 8 over 2 minus 2, which is 0 over 0. And from 0 over 0, we could determine nothing. Other than this, right, what we can determine, we can't determine the limit, right? What we can determine is, let's get this stuff out of the way here. We can determine that since putting 0 in for x in the denominator gives us a 0, putting 2 in for x in the denominator gives us a 0, we know, and it's quite obvious actually, that x minus 2 is a factor in the denominator. But also because we put 2 in for x in the numerator and got 0, we know that x minus 2 is a factor of the numerator. And so we could factor this farther and have x plus 4, so x minus 2 divided by x minus 2 is equal to 0 for all values of x other than at x equals 2. And so we're approaching 2 plus 4, or 6. And so our limit, therefore, is 6. Okay, we had other ways that we could keep going, right? In number 2, if you recall what we did to handle this, I'm going to make this a little bit thinner. What we did to handle this is we multiplied top and bottom of this fraction both by the conjugate, and so that we have the limit as x approaches 4. My numerator is going to be the square root of x plus 5 times the square root of x plus 5, which is simply x plus 5. Happens every once in a while. Plus 3 times the radical minus 3 times the radical. Those are going to cancel, and then minus 9. And notice that that numerator, 5 minus 9, is negative 4, so our numerator is x minus 4. Our denominator still has the factor of x minus 4, and it's now multiplied by the square root of x plus 5 plus 3. Okay? And so we can factor out the x minus 4 from the top and bottom, and we're left with 1 over the square root of x plus 5. So we have the limit as x approaches 4 of 1 over the square root of x plus 5 plus 3. So that now, when I take that 4 and substitute the 4, I'm going to get x plus 5, which is 9, plus 3. And so the square root of 9 is 3. So I have 1 over 3 plus 3, or 1/6. And so that limit is 1/6. Okay, so that's kind of nice. Now, number 3, if we recognize that e to the 2x is e to the x squared, let's fix that. That's going to be e to the x minus 1. We can recognize that that numerator will factor as e to the x minus 1 times e to the x plus 1 divided by e to the x minus 1. These will cancel. We put 0 in for x. We're going to get e to the 0, which is 1, plus 1. So we have 2. Now, each of these are indeterminate forms, because when we put 0 in for x, we're going to get 0 over 0. In all 3 of these cases, we're going to get 0 over 0. So a while ago, a French mathematician by the name of L'Hopital comes along, and he says, you know, there's another way that we can handle these things. He says, you know, if we look at these indeterminate forms and we look at what we've got is the limit as x approaches infinity of f of x divided by f of x, if we have the indeterminate form, then the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator remains unchanged. Okay? This works only when we're approaching 0 over 0 or infinity over infinity, okay? I keep doing that. So let's look at an example here. Let's look at number 4. Now you'll notice example 4 is similar to the number 1 we already did. 5 and 6 are similar to number 2 and 3. Actually, they're not similar, they're the same. So again, if I put 2 in for x, I'm going to be approaching 0 over 0, which is indeterminate. I can't determine anything from that. What L'Hopital says is that I can take the derivative of the top, because this is in an indeterminate form. I can take the derivative of the top, which is 2x plus 2, divided by the derivative of the bottom, which is 1, and now evaluate as x approaches 2. 2 times x, which is 2, plus 2 over 1, and that would be, that's not 4, and that would be 6. Now let's scroll back up. Is that what we got here? We got 6. Okay, so notice that we'll get the same thing. Now, example 5, okay, example 5, I'm going to rewrite that as the limit as x approaches 4 of x plus 5 to the 1/2 minus 3 over x minus 4. And again, let's remind ourselves, when we did the limit using the rules we know, we got 1/6. So let's check that out now if I use L'Hopital's rule, because again, if I put 4 in for x, 4 plus 5 is 9. The square root of 9 is 3. 3 minus 3 would be 0. And 4 minus 4 would be 0. We have 0 over 0. So we can invoke, I'm going to call it invoking L'Hopital's rule, and say, therefore, that we can simply take the derivative of the top and the derivative of the bottom. So we have the limit as x approaches 4 of the derivative of x plus 5 to the 1/2. That's 1/2 times x plus 5 to the negative 1/2 plus 0, because the derivative of negative 3 is 0, divided by the derivative of x minus 4, which is 1. Okay? And so we have now the limit as x approaches 4. I'm going to go ahead and write this as 1 over 2 times x plus 5 to the 1/2. So it's 1 over 2 times 4 plus 5 to the 1/2. 4 plus 5 is 9. The square root of 9 is 3. So we have 1 over 2 times 3, or 1/6. And again, notice that that is the same as the limit we would have gotten before. Okay. For this course, I'm not going to take the time and prove L'Hopital's rule. Not necessary at this point. I'm going to just try to encourage you to learn and be able to use L'Hopital's rule. Again, number 6, we showed that if we put 0 in for x, we're going to get e to the 0 minus 1 over e to the 0 minus 1, which is not 1, because e to the 0 is 1, both on top and bottom, and we get 0 divided by 0. Okay, so what we notice is that we don't have a determinate form where I can determine this is what the limit is. We have the indeterminate form, 0 over 0. And so I now can find the derivative of the numerator. The derivative of e to the 2x, the derivative of e to the u is e to the u du divided by the derivative of the bottom, which is e to the x. Derivative of e to the x is e to the x. And so now you'll notice that as x approaches 0, we're going to have 2 times e to the 0 divided by e to the 0, and e to the 0 is still 1, and so we have 2. And again, if we were to scroll back up, when we found the limit using the methods we had before, the limit was 2. Okay, so L'Hopital's rule is really nice. It's going to save me work. And one thing is, it's going to save me some effort when I'm in situations that I was in previously where I didn't want to have to factor. It's also going to work in other cases where factoring is impossible or at least is not desirable. Okay, so the first thing, though, you always want to check, like in number 7, you do need to verify what the limit will be. Now, e to the 2 times 0, 2 times 0 is 0, e to the 0 is 1. So we have 1 minus 1 over 0 equals, 0 over 0, which is an indeterminate form. L'Hopital's rule will only work when you have an indeterminate form, 0 over 0. Okay, actually, and this is mentioned above, you may have noticed, I may have skipped over it, that L'Hopital's rule will work not just when you have 0 over 0, but also infinity over infinity. And the signs don't matter. Okay, so 0 over 0, infinity over infinity are the two situations where L'Hopital's rule will work. Okay, so now since I have 0 over 0, I know that I can find this limit using L'Hopital's rule. And so I have the limit as x approaches 0. The derivative of e to the 2x, I suppose I could cheat and look over here at number 6 to the left, but the derivative of e to the u is e to the u du, and the derivative of x is 1. See, this one is a case where I'm not sure I would want to have to try to tackle at number 7, try to tackle finding, how do I factor that out? I could, like I did earlier in number 6, when we did it up before as number 3, I could factor e to the 2x minus 1 as e to the x minus 1, e to the x plus 1, but still factoring out that x is a bit of a challenge. L'Hopital's rule frees me from having to do that. So now as I put 0 in, I have 2 times e to the 2 times 0 over 1, and that's just going to be 2 times 1 over 1, which is simply 2. Okay, so L'Hopital's rule isn't bad. It's kind of nice, actually. Now, in number 8, the limit as x approaches 5 from the left, right? If I put in 5, I'm going to have 25 minus 25 is 0. 5 minus 5 is 0, so I have L'Hopital's rule. Again, before I invoke L'Hopital's, though, I'm just going to rewrite 25 minus x squared to the 1/2. And so now the derivative of the top is 1/2 times 25 minus x squared to the negative 1/2 times the derivative of what's inside, so negative 2x. Okay, don't forget your chain rule. And now I'm going to divide that by the derivative of x minus 5, which is simply 1. Okay, so I have the limit as x approaches 5 from the left. And let's rewrite this as a fraction. We got the 2 is going to go down here. The square root of 25 minus x squared goes down here, and the negative 2x is up top. I suppose I can do that if I want to. Now, as x approaches 5, we're going to have 5 over the square root of 25 minus 5 squared, 5 over 0. Now, 5 over 0, don't forget about the 5 over 0, right? That means we're approaching an asymptote. We're approaching a vertical asymptote, right, when the denominator only is 0. So we're either going to be approaching positive infinity or negative infinity. Okay, so we're approaching a vertical asymptote. Which direction are we approaching from? So I do need to remember, though, that my denominator is getting closer and closer to 0, but notice it's the positive square root, right? X values are slightly less than 5, so this is slightly less than 25. So my denominator is slightly bigger than 0. It's positive. So this would be going off to approaching 0 from the right. And so our limit is positive infinity. Don't forget your other limit rules. Okay. Now, number 9, we've done the limit here before, and we know that this is going to approach, like, as x goes off to infinity, my numerator is going to get infinitely large, and my denominator is going to get infinitely large. We've explored those things in the past. I should not have to reteach you the things that we were responsible to have learned in the past. And again, infinity, getting infinitely larger divided by getting infinitely larger, right? A quantity 5x plus 3 that's getting infinitely larger, divided by the quantity x cubed minus 6x plus 2 that's also getting infinitely larger is not necessarily going to be approaching 1, because notice that they're getting infinitely larger at different rates. The denominator has an x cubed. It's going to be approaching infinity much faster than the numerator, so we can actually think about that, right? So if I take my limit using L'Hopital's rule, the first thing I'm going to do is I'm going to find the derivative of the top, which is 5, divided by the derivative of the bottom, which is 3x squared minus 6. And now notice that as x goes off to infinity, my denominator is getting infinitely large in a positive direction, but my numerator is not changing at all. So I know that our limit is 0 because we have our denominator that's getting infinitely larger, and our numerator is not changing at all. So our limit is 0. Okay. Number 10. Okay. Sine of x, as x goes off to infinity. Oh, this one's kind of interesting. The sine of x is actually going to oscillate between -1 and 1. Okay. As x goes off to infinity, my denominator is approaching infinity because x is getting infinitely large. I can use L'Hopital's here and say we have the limit as x approaches infinity. The derivative of sine is cosine x. The derivative of 1 minus, I'm sorry, the derivative of x minus pi is 1. So we have the limit as x approaches infinity of cosine of x. Now the limit as x approaches infinity of cosine x actually goes back and forth between 1 and -1, which tells me that I have a bit of a typo here, right? So let's fix something. Let's suppose that what we wanted to do was not find the limit as x approaches infinity, but find the limit as x approaches pi. This will make more sense. So if I'm going to find the limit as x approaches pi, we're approaching sine of pi divided by pi minus pi. The sine of pi is 0, and pi minus pi is 0. Okay. And so now I'm going to take the derivative. The limit as x approaches pi, the derivative of sine of x is cosine of x still. My derivative of x minus pi is 1. And so we have the cosine of pi, which is -1. Never thought you'd use that unit circle, did you? Okay, number 11. Moving right along here. Number 11, again, notice as x approaches infinity, my numerator is getting infinitely larger, and so is my denominator. So I can use L'Hopital's rule. So I have the limit as x approaches infinity of 4x to the third divided by 3 times the derivative of e to the 2x. The derivative of e to the u is e to the u du. So I have the limit as x approaches infinity of 4x cubed divided by 6 e to the 2x. Now I suppose I could reduce the 4 and the 6. I'm not going to bother. Okay, not at this point. Notice though that my numerator, okay, is still getting infinitely larger. As x goes off to infinity, 4x cubed is getting infinitely larger, and so is 6 e to the 2x. So this is still approaching an infinity over infinity, which means that L'Hopital's rule actually still applies. So I can do the derivative again using L'Hopital's rule. And the derivative of 4x to the third is 12x squared. The derivative of 6 times e to the 2x, well, again, the derivative of e to the u is e to the u du. So this can be 6 times. Okay. Notice x squared is still going off to infinity. E to the 2x is still going off to infinity. So I'm going to have 24x divided by 24 e to the 2x. My numerator is still going off to infinity. As x approaches infinity, 24x is getting infinitely larger. And 24 e to the 2x is also getting infinitely larger. So that's an infinity. So I take the derivative. I'm going to only be able to do this, I believe, maybe one more time. Give myself a little bit more room here. So the limit as x approaches infinity, the derivative of 24x is 24. The derivative of 24 e to the 2x is 48 e to the 2x. Now notice that 24 is staying constant. E to the 2x is getting infinitely larger. So my denominator is getting farther from 0. My numerator is not. Therefore, we know that what we're approaching, therefore we know that what we're approaching is 0 over infinitely increasing values, or approaching 0. Now this one I could have seen coming if I practice with these enough. Notice that every time I take the derivative, right, x to the fourth becomes x to the third. The derivative of that is x squared. The derivative of that is x to the first. So those power functions, x to the fourth, every time I take the derivative, the degree decreases by 1. But e to the 2x, the derivative of e to the u is e to the u. So the derivative of e to the 2x is going to stay as an e to the 2x. That's going to be multiplied by 2 each time. So this coefficient is getting larger, but that's irrelevant. The e to the 2x will remain. So I could see that that was going to be a 0 if I practice with these. Okay. I might suggest here that you pause the video, depending on where you're watching this and how much time you have and what's going on around you. But at some point, I would recommend that you pause it and go do a few practice problems where the limits are approaching either 0 over 0 or infinity over infinity. And you will have, sorry about that, and you will have a idea of how to handle the basic L'Hopital situations. Okay, so I'm going to assume that you did take some time and practice. Excuse me. And I'm going to look at some more forms that we can see with L'Hopital's rule. So the first thing they're going to point out is the indeterminate forms that I've mentioned, 0 over 0 and infinity and over infinity, those are indeterminate forms. However, those are not the only indeterminate forms that I might find or that I might encounter. Okay, I may also encounter a form that's 0 over 0. I'm sorry, in addition to 0 over 0, I might also encounter 0 times infinity, 1 to the infinity, 0 to the 0, infinity minus infinity. Now, we tend to think a little off here, so let's talk a little bit. If I've got something like 0 times infinity, I don't mean I have the number 0 times an infinitely large value. What I mean is I have one function that's approaching 0 and the other function that's approaching infinity. So we're never actually multiplying by 0. Okay? If I have the form 1 to the infinity, I've got a function raised to another function. The function that's the base is approaching 1. It doesn't equal 1. I know that 1 to the 5th is 1 and 1 to the 8th is 1 and 1 to the 12th is 1. But the base, the function that's giving me the 1, and we'll get to here in a little bit, but that value is approaching 1. The exponent is approaching infinity. So keep that in mind. We don't have the value 1 or the value 0. We're approaching those. So let's look at number 12. What you'll notice in number 12, okay, is as x approaches infinity, e to the negative x, as x approaches infinity, e to the negative x is approaching 0. As x approaches infinity, the square root of x is getting infinitely large. And we have the function e to the negative x that's approaching 0. We have the function, the square root of x, that's approaching infinity. We don't actually have 0 times infinity. Okay? So the solution here to get out of this is actually fairly simple. E to the negative x multiplying by e to the negative x is the same as dividing by e to the x. Right? So really what I'm going to do is the function that's approaching 0, I multiply by its reciprocal, or the function that's approaching infinity, I multiply by its reciprocal, depending on the scenario in which is going to be easiest to handle in that particular setting and situation. Okay. In this case, it's easiest to say, let's change e to the negative x to dividing by e to the x. So now, as x approaches infinity, the square root of x is getting infinitely larger, and e to the x is getting infinitely larger, and those two things are approaching infinity. Okay. Now, when I talk about looking at the rate at which they're approaching infinity, if you think about the function the square root of x, we all know that it looks something like this. We all know that e to the x looks something like this. So my numerators are getting infinitely larger, but at a slower and slower rate. My exponential function e to the x is getting greater and greater and greater. So that should kind of give me an idea of what I expect this to happen. So my numerator is going to be getting larger. My denominator is going to be getting larger, but my numerator, the square root of x, will be getting larger at a slower rate. But now that we have an infinitely increasing value divided by an infinitely increasing value, we're in a form, we've already put this into a form now that we can invoke L'Hopital's. So if I take the derivative of x to the 1/2, that's going to be 1/2 x to the negative 1/2 divided by the derivative of the bottom, which is e to the x. Now interject the thought here. Some people, some of you, are still wrestling with the quotient rule in a recently graded test. I saw a number of people that when they're finding the derivative of a function divided by a function are just taking the derivative of the top and the derivative of the bottom separately. That's not the quotient rule. That won't find for you the derivative of that function. Notice that what L'Hopital's is accomplishing for us here is not finding the derivative of a function. What L'Hopital's is doing for us is it's helping us find the limit as x approaches some value. So L'Hopital's is for taking limits. So now, if I think about this, whoops, this is, I'll get my eraser here, the limit as x approaches infinity of 1 over 2 times the square root of x times e to the x. Now, so you'll notice that as x approaches infinity, the square root of x is approaching infinity, e to the x is approaching infinity. So my numerator is staying 1, and my denominator is getting infinitely large. If my denominator is getting infinitely large, it should follow, and my numerator is not, we all know that means that we're approaching 0. So that limit is 0. Okay. Number 13, okay, we're multiplying by the cotangent of x. As x approaches 0, x cubed is approaching 0, but the cotangent of x, if you remember what the graph of that looks like, that would be approaching infinity. I have a 0 times infinity. What I did here is I had the function that was approaching 0, and I moved it to the bottom. In this case, the function that's approaching 0 is going to stay on top, and the function that's approaching infinity is the one I'm going to move to the bottom, because if you recall, cotangent is the reciprocal of tangent. Okay, so since cotangent is the reciprocal of tangent, multiplying by cotangent is the same as dividing by tangent. So now we're approaching 0 over 0. And so using L'Hopital's rule, the limit as x approaches 0 from the right, that's going to be 3x squared divided by the derivative of tangent. The derivative of tangent is secant squared. Now you remember that secant is the reciprocal of cosine. So let's do another thought here. Dividing by secant would be the same as multiplying by cosine. You got to learn your trig identities. Okay. So dividing by secant is the same as multiplying by cosine. Dividing by secant squared is the same as multiplying by cosine squared. So now there are no fractions. So I can't even dream about using L'Hopital. As x approaches 0, I really should remember that the cosine of 0 is 1, And so we're going to have 3 times 0 squared times 1 squared. It doesn't really matter. That limit is also going to be 0. I'm getting 0 frequently here, but that's okay. So what? So what about number 14? Okay. For sake of time, I'm going to leave number 14 for you to practice. And remember that the tangent, okay, what does that equal? How do I handle that? Okay. So try number 14 on your own. Take a break. Okay. So isn't it, I'm going to assume you tried number 14, and for sake of time, so this video doesn't drag on too long, I'm going to move on to number 15. Because when we get to these forms, things get a little bit different, a little bit weird, okay? So we have the limit as x approaches 0 of e to the x plus x all to the 2 over x. And the question is going to be, how do I handle that? Because you'll notice that we have an exponent there, and L'Hopital's rule doesn't allow for exponents. Okay, so how am I going to do this where I need to allow for the exponent? How do I get an exponent out? How do I handle bringing that exponent down? Okay, basically, right, I can hear you all nodding. That means, yes, goody goody, we get to use logarithms. Basically, what we're going to say is that y is equal to the limit as x approaches 0 of e to the x plus x to the 2 over x. Okay. Next, we're going to take the natural log. We've done this before. We're going to take the natural log. Now here's where I have trouble writing. The natural log of the limit of e to the x plus x to the 2 over x. And we've also explored this in the past, that if I have the natural log of the limit of a function, that's equal to the limit of the natural log of that function. Okay. So the natural log of y is equal to the limit as x approaches 0. Now this is going to be 2 over x times the natural log of e to the x plus x. Plus x. This is getting sloppy. Natural log of e to the x plus x. The natural log of e to the x plus x, so we're approaching 0 from the right. The natural log of 1, Okay, so what you'll see here is that we have the limit as x approaches 0 of 2 times the natural log of e to the x plus x over x. As x approaches 0, we're going to have the natural log of 1, which is 0, divided by 0. So we're approaching 0 over 0. We have a limit approaching 0 over 0. Since we have a limit that's approaching 0 over 0, we can invoke, you guessed it, now we can invoke L'Hopital's rule. So the limit as x approaches 0 from the right, so the derivative of 2 times a function is 2 times the derivative of the natural log of e to the x plus x. And the derivative of the natural log of u is 1 over u du. And then the derivative of this x is just 1. That's fortunate. So now this is going to be 2 times e to the 0 plus 1 divided by e to the 0 plus 0. So that's 2 times 1 plus 1. That's going to be 2 times 2, which is 4. E to the 0 is 1 plus 0 is just 1. So that limit is 4. Now, we're not done, though, because notice it's the natural log of y. It's the natural log of y that equals 4. That's an e. If the natural log of y equals 4, then y equals e to the 4th. Okay, so L'Hopital's rule, I mean, finding those derivatives, those limits can be a bit exciting. Okay. All right. Number 16. Okay. I would do this the same way. I'm going to use a different color here just because I'm afraid I'm going to run into this. So y is equal to the limit as x approaches infinity of 1 plus 1 over x to the x. Now you'll notice that as x goes off to infinity, we're approaching 1 to the infinity. So we've got a function 1 that's getting infinitely raised to a power that's getting infinitely larger. 1 plus 1 over x is getting closer to 1. It's not 1, it's getting closer to 1. Okay. So I'm now going to take the natural log of both sides. So that, that's a y. The natural log of y now, I can reverse my limit and my natural log. Okay. Move this up, and I realize we lost part of that, but that's okay. So the natural log of y, let's fix that. The natural log of y is equal to the limit as x approaches 0. Now we're going to have x times the natural log of 1 plus 1 over x. Now notice as x approaches 0, this is approaching 0, this is approaching the natural log of 1, which is 0. Okay. So actually, I take that back. This is getting infinitely large. So we've got 0 times, this is approaching 0, this is times infinity. So we have an issue there. So this is going to be a neat little trick. You ready for this? What we're going to do is we're going to, instead of multiplying by x, we're going to divide by 1 over x. Okay. So one more step before I invoke L'Hopital's. We've got the limit as x approaches 0 of the natural log of 1 plus x to the negative 1 over x to the negative 1. So now if I take the derivative, using L'Hopital's rule, the derivative of the natural log of u is 1 over u du. Okay, now I'm going to divide that by the derivative of x to the negative 1, which is negative 1 x to the negative 2. And so this now is 1 over 1 plus 1 over x, the natural log of y. Whoops, I forgot to write my limit as x approaches 0. So this is my limit as x approaches 0. Now if x is approaching 0, x is not approaching 0. I've been writing 0. It's infinities right from the beginning. It's infinities. I apologize for that. As x approaches infinity, 1 over x is approaching 0. So if this is approaching, fighting with my pen here, if this value is approaching 0, we got 1 over 1, so we should be approaching